So again, welcome to this six-part webinar series. My name is Born Vaccarello. For those of you that do not know me, I did my bachelor's at the University of Toronto. I did my PhD at the University of Texas at Dallas. I then moved to Adelaide. I did a one-year postdoc for CO2 CRC at ASP, and then I was a lecturer for a couple of years. This is where this project got started. This was all the way back between 2006 and 2008. Kind of a unique thing about me these days is that I combine expertise in sedimentology and sequence stratigraphy with web technology. So a lot of the stuff that we will be looking at is kind of combining both how depositional systems work and what their architecture is with how can we actually visualize kind of the important components and how we can build systems that help us make decisions when we work with these systems. We will have 6 webinars. Today's would be our intro webinar. Next webinar would focus entirely on characterizing depositional environments, kind of highlighting some of the new dashboards that we have put together. We will then have a deep dive into depositional environments. We will have a fluvial-dominated, wave-dominated, and tide-dominated sessions focusing on the various analogs that we have as part of the database. And then we'll finish off with a webinar that focuses on channelized intervals. In terms of objectives for the webinar series, the first thing that we want to do is we want to familiarize ourselves with Sedbase. Again, this is kind of the main objective of the webinar. So learning how, for example, the classify environments dashboards work, learning how to view analogs and dimensional data, and then also how to build conceptual models using our digital whiteboard. Something else which we want to learn is we want to learn the language of the database, and we want to understand the notion of depositional hierarchy. So at what time should we be interested in different scales of depositional environments to answer the particular questions that we want to answer. We want to get hands-on kind of knowledge and understanding of how we can use, for example, the characterized environments dashboard to answer questions about depositional environments. We have quite a few different things in these modules that you can actually use, interactive image atlases, decision support systems, etc. We then want to do deep dives into fluvial-dominated, wave-dominated, and tide-dominated environments, heavily relying on our quite extensive database of analogs that we have put together. So a lot of these lectures would heavily be building on our own data to illustrate, what are the key architectural things that we need to worry about when we think about these systems. We will do the same with fluvial environments. In quite a few places in the webinars, you will be seeing a lot of kind of 3D conceptual models like this, which are very useful for us to kind of get to understand the key features that we need to be interested in terms of architectural complexities of these deposits. And the last thing that we want to do is we actually want to learn how to extract dimensional data, how to find it in Sedbase, and how to use it. So altogether, all of these features, everything that we are discussing and everything that we will be discussing throughout this webinar series, you can think of it as a set of kind of helpers that make us decisions in the subsurface. So for example, we will have characterization tools, using depositional analogs, using dimensional data, using depositional mental models. So again, having the right thinking of depositional systems in the right way so that you make the right choices in the subsurface. You do all of this and you apply it to typically limited data scenarios in the subsurface. This is really what we are after. Typically in a subsurface scenario, there is never enough data to properly characterize the architecture. You always have to deal with uncertainty. And the better you deal with it, the better you will then be able to reflect all of these decisions into the static modeling that you do, into the dynamic modeling that you do. Okay, so these are our objectives. Let us then move on with kind of the official part of our first webinar, Introduction to Sedbase, can it help you? So before we get into the content, let me, again, for those of you that are not familiar, let me go over our history so that we can understand a bit better where the project comes from. The Sedbase project got initiated as the WAVE Consortium, which was run out of the University of Adelaide at ASP. So this happened between 2008 and 2015. About 10 years ago, and it moved on kind of to a setup with a private company, Sedbase. And the product has greatly expanded in that period. And the last thing that I want to mention is that in the last couple of years, we also kind of had a major effort to redesign our somewhat dated pages that were there previously. A lot of the software that we have in Sedbase, since it started from 2008, you can imagine that the technology has changed a lot. So everything that we have now it uses a single page application design. We have fully moved to the cloud, so we use AWS in the backends. So what we have now is pretty much kind of a modern platform designed for this, and quite a few companies have participated in the project over the years. So what is Sedbase? We can think of Sedbase as a cloud-based platform. So it's something which is accessible on the web. It is there to help us improve decisions about shallow marine and fluvial deposition architecture. So these word decisions there is key. And we're mostly focusing on subsurface applications. So in the subsurface, we typically have limited data. How can we use this limited data so that we can make the best possible choices and the best ways to characterize the uncertainty that might be there in the parts of the data that we cannot see? And kind of a core of Sedbase is dealing with exactly what I just said, this limited data problem. So typically in the subsurface, we would, let's say that this is a field that you're dealing with. Typically you would have wells which are kilometers apart. There can be a lot of things happening in these areas which might have very little data associated with them. So in this case, imagine that you have a couple of wells. You can characterize the wells themselves. You can work out what the depositional environment is, but you always have the question of, what is in between? How big are the various architectural units that we are mapping? Is there something that we are not seeing? So there is always a big element of prediction of stratigraphic architecture between wells, and especially in shallow marine. The unfortunate thing is that we will very often fall in this kind of, we will have limited data. Very often our intervals will be below seismic resolution. Typically we will not have sufficient amount of data to only use geostatistics in an interval. So for example, in the coal industry, they can easily get hundreds of wells to characterize an interval. In this case, you can easily just use geostatistics and you would solve everything. But very often in the types of data that we deal with, there would never be enough wells. There can always be a lot of question marks in between. So Sedbase really kind of tries to fill this niche and tries to answer some of these questions. How can we properly handle the uncertainty where a lot of time we would not know what the answer is? So there will be significant stratigraphic uncertainty. And of course, if you make the wrong decisions early on, so if you do a poor job of characterizing this uncertainty, all of this propagates through a project. So you can make decisions early on, which can then, for example, lead to incorrect deposition or characterization, poor static modeling decision, misleading dynamic modeling results, and then the important stuff that follows. So you might have wrong volumetric estimates, the wrong well planning decisions, wrong economic forecast. So the key is that very often the sort of stratigraphic architecture decisions that we make early on in the project, if we don't do a good enough job early on, a lot of those things can propagate through the projects. Of course, all of this should be fairly straightforward and intuitive. So how can Sedbase help with this problem, with this limited data problem? Well, we have quite a few tools that can be used to address some of these issues. So imagine that we have subsurface data. Well, with this subsurface data, we can interpret its environments. We have tools that would help us with that. We can use depositional analogs. We can use dimensional data. We can use depositional knowledge. Even this webinar that we are kind of running right now, all of you would have access to it afterwards. You can go back to it. And once we start talking about the depositional environment sections, there will be a lot of useful stuff there which would help you make kind of the right decisions about stratigraphic information. And then ultimately and ideally, we will take all of this information together and then we will start thinking about, what conceptual depositional models from a reservoir standpoint represent the interval. And then it should be these conceptual models that start kind of driving our static and dynamic modeling efforts. So hopefully kind of all of this early on then makes its way through the final outputs. Just to illustrate how something like this works, if you go to the documentation page, which I showed you just in the beginning, this is the main page of the documentation page. If you click here on shallow marine workflow, there's actually a workflow, a fairly detailed workflow, which you can use to help you kind of understand how Sedbase can fit in the type of work that is typically done in a subsurface project. So let's actually go through this very quickly, not going into any detail at all, just to give us a feeling for how all of this can work. So there will always be steps that we will do before we ever start using Sedbase. So we always have to identify clearly what the problem is. What exactly do we want to model? What type of a question do we want to address? We will then evaluate the subsurface data. We always want to know what the tectonic setting is, what the regional depositional setting is. Any kind of regional scale information is very useful to know before you ever start using Sedbase, because you might want to use some of this information to actually confine, for example, types of analogs that you will be going after. We then would do, let's say, the sequence stratigraphy of the interval, kind of subdividing it into regressive and transgressive packages. We will start thinking about placing boundaries of individual facies associations, and then we'll start thinking about making depositional environment interpretations of these facies associations. Well, in these sections, Sedbase does have a lot to offer. So we have tools that can, for example, help you interpret core, identify lithofacies, identify ichnogenera. We have integrated atlases as part of our packages. We have integrated facies models that you can use to, again, help you with some of these decisions. We have plenty of tools that can help you interpret the depositional process of an interval. So all of these things would be in this characterized environments application that we will be discussing and spending a fair bit of time on today. Okay, we then move on. The next question that we want to ask ourselves is what happens between wells? So what is our inner well architecture? And then how do we take all of this information and build conceptual reservoir models that we might want to model? Again, there is plenty of stuff in Sedbase that you can use for these two steps. This is, in a way, probably the most difficult part of the entire process, because this is where you can make all of these important choices, and this is where you would constrain your models deterministically, considering possible variations of depositional environments, possible scenarios that you can run. So you can use our characterized environments application. You can use our view analogs and dimensional data applications, to view analogs, get dimensional data, get feeling for dimensions of things. There's plenty of stuff in the Sedbase documentation that can help with some of these steps. Even this workshop itself is kind of something which can be used. We also have this digital whiteboard that we mentioned. Okay, you would then want to kind of start thinking about the modeling design of your static model, and then you would want to build your static model. Well, if you're interested in dimensional data, we also have that. So if you want to build, for example, if you want to do object modeling of channels, you can go to Sedbase and get these data. And then kind of finishing off at the end, you will build a property model, do upscaling, dynamic model. This is once again where we start kind of going outside of realm of Sedbase. So hopefully this is helping you where exactly Sedbase typically would fit in a subsurface project. Okay, so Sedbase overview. I did show you some of this already right in the beginning of the lecture. So as I mentioned, we do have a new public web page. We do have this documentation section, which again, it is very useful that it is there. So if you're, for example, curious about how to sign up to Sedbase, now you can directly go in there and find the appropriate page and it will tell you. To get in, you would click on the sign in button. Now, two different things can happen here. If you already have an account, so if you have already signed up to Sedbase previously using our different version of the software, a lot of the authentication kind of technology that we use on the back end is the same. It has not changed. So you still have your username, you still have your password. All you would have to do is you would use your work email, you would use the password that you set up when you originally signed up, and you would go in. Now, important, if you are new to Sedbase and if you want to sign up for a first time, this is the page that you would see. You have to click on this button on the bottom, sign up, which will take you to a slightly different version of the page, where you would again put in your work email. You would select your own password. There will be a little pop-up that shows you that explains what type of a password we are expecting in terms of security. So you would put that in. You would click the sign up and get authorization, your authorization code button. Now this is important. There will be an additional step here. So you will get an email from us, and the next time you log in, there will be a place where you would enter a code, which is, and all of this is described in a fair bit of detail in our sign up document that is available on the public documentation. So you do this, you then get in and you're already in Sedbase. The default view now is this one. So the default dashboard that is shown is this characterized environment dashboard. Now, what this does is it incorporates several of our previous modules that we had in the previous version of Sedbase. So we had quite a few, for those of you that have been there before, we had a selection of quite a few different classify module types that you can choose from. Now everything has been integrated together in a single dashboard. All of the data sets talk to one another, so you can all use them at the same time, which makes this a lot more powerful and a lot more useful. So in terms of the things that you will see here, on top, there will be your top panel. This is where you will be selecting what type of a dashboard you're interested in. Right now, we are in the characterized environments dashboard. On the left-hand side, in all of these dashboards, you would have kind of filters that you can use. You can add as many of them as you like. They all talk to one another. So in this case, you have quite a few different ways in which you can, for example, select the depositional process of an interval. And then the main part of the page will be your display area. Okay, so in a way, you're using the filters on the left to filter for data. And then depending on what dashboard you're in and what part of the application you're in, different things would be shown in the display area. Very often you'll be able to interact here as well, so you can actually click some of these buttons. So let us kind of have a deep dive into the characterized environment dashboard. Again, we are in this part of, this is the active dashboard at the moment. Let us start off with an example. We have all of these filters on the left-hand side as we were discussing. All of them would have buttons, text boxes, radio buttons that you can use. The very first filter is also one which is being used in our depositional environment, in our analogs and dimensional data dashboard. So you can select a process. Let us do that. In this case, we have clicked WF. You would notice that quite a few things in the display area changed. On top, we get a summary of what is basically happening. So we have one filter which is being selected. we're being told the number of possible processes that correspond to that filter, the number of possible local environments or element complexes which can be true in this case. You'll notice that this ternary plot has one part of it, WF, which has turned green. So green means this is an active filter. So we're being told what we just put in. We're being told that we have one active process now, which is WF. So this is an interactive plot. We would scroll down in the page. Lower down, we have this new pie chart view that has been added to the latest version of the product. And what this is telling you is that we have, in this case, we are lumping element complexes by type. So in this case, we are being told that you have 3 types of element complexes that have been returned as true. And for each type, we have the processes which are associated with it. The ones that are valid are shown in green. So in this case, we're being told that we have a mouth bar, a lobe, or a beach element complex as a possible solution. And in each case, this would be the process associated with it, WF. So this is this pie chart view. Now you can click on the grid view, which is the thing which we have always had. So we have both of those options. You can quite easily switch back and forth between them. They talk to one another. So if you click on the grid view, you kind of get the more standard appearance of something that you would have been used to. So once again, in this case, in green, we are showing the valid answers, WF mouth bar, WF lobe. In this case, all possible element complexes are shown. We can actually limit these by these interactive menus on top. So if we select local and nearby only, we would only get the 3 answers that were selected, and they are siblings. We will talk about what these siblings are in a little bit later in the presentation. In all these cases, every element complex has this hand lens button, which is again something which we had in the previous version. If you click on a hand lens button, you would get an interactive page that pops up, kind of a pop-up window, which would have a faces model with text explanation below it. So the idea is that you can, in fact, work with a page like this. You're being given a number of possible answers. This is where decision-making comes into play. So you have to make a decision about, is this interval that I just classified as wave-dominated fluvial influenced? Is this a mouth bar? Is this a beach? Can this be part of a delta lobe? Can I actually tell? This is where you will start looking at some of these faces models to potentially, again, help you with making some of these choices. So you can always take out some of these options. Okay, so you'll close the window, and again, this is where we are. We have selected one filter, and we have a display area which has updated. So this is one active filter. Now, something which we should be mindful of is that we have a number of different filters. In the previous version of Sedbase, each filter was its own set of pages, its own module. Now everything works together. So in this case, we have selected manually WF, and the dashboard has been updated by that. An alternative way of actually getting the same result is putting in percentages, which is again something which we had before. This was its own separate module. Now it is just part of the dashboard. So if you put in, let's say that the interval has 70% wave-dominated faces and 30% fluvial-dominated faces, we will get the same result. We will get WF. There is a filter called characterized process uncertainty. Again, this is something which we had as a standalone module in the previous version. All you do in this case is you tell the database which processes are present. This is the thing with the check mark. Which processes are absent. This is the X. So in this case, we are saying that we have fluvial, we have wave, we do not have tide. And we are also telling the database that our wave process is the dominant one. Well, this combination gives you WF again. So notice that all filters now can be used at the same time, that they all work together. our entire modules from before, which were standalone modules, have been integrated kind of into a single solution. It works a lot better. It's a lot easier to use. Now notice that with, for example, this filter, if we change the menu, so if we move the selection from no tights to we are not sure if there is tights, this is this question mark. The moment we click there, everything is going to update on the right-hand side. So all this works fairly quickly. So you can very easily change filters, change your mind, see what making a change would kind of seeing what result it would cause. All of this works fairly easily and intuitively. Now, something else that you can do with all these modules, this is not only a display, this tertiary plot, this is actually buttons as well. So in fact, if we click on WTF in this case, and if we don't like this category, we have taken it out. So over here, you can see that our summary kind of little cell is telling us that we have removed one process. So the moment you remove this process, all of the other results would be updated. So this is one filter. As I mentioned before, we can use these filters together. We can, in fact, very easily add this filter, the one that we just had. And if we add a second filter and we only put in WF, you will notice that this green field here disappeared. It disappeared because we are adding two filters together. The first one is giving us more result, but the second one that we added is restraining things. And now we are back to a single answer. Okay, so again, all of these filters can be used together. This becomes very powerful once we start talking about kind of the other parts of the filter menu, which deal with physical structures and technology. So everything that we had before as standalone modules now seemingly integrates together. So all filters can be used at the same time. Okay, so right now we are in this classify by identifying the positional process section of the filters. If we click on this drop-down button, we can deselect the drop-down button. And if we go on to the next one, classify by identifying physical structures part of the page, we open a new filter. Now, this part of the filter is again a different module that we had. This one had to do with directly using physical structures, kind of identified physical structures and their proportions to come up with a set of answers by a very big kind of tables of rules that we have in the background. So how does this work? In this case, we work by lithology, so we will do sandstone, heterolithic, and mudstone separately. If we click on sandstone, so if you click on these buttons, basically the filter would expand and you would be able to answer questions about each lithology separately, but let us do sandstone now. So in this case, we are clicking on this Add Structures button. This opens a pop-up window, which has a list of physical structures kind of given to you by us. We again have hand lens buttons here. So if you click on a hand lens, you actually see an integrated image atlas. So in all of these cases, you can very easily, for example, if you have doubts about the physical structure that you're observing and what you want to call it, there will always be images that you can use to help you make some of these decisions. Okay, so be mindful of that. We have an integrated, basically physical structure image atlas as part of the application. Again, this is something that we had before in the previous version of Sedbase as well. So we scroll down. In this case, we would select a couple of categories. So we have selected trough cross stratification and hammock or swaley cross stratification. We have put in percentages. So in this case, we are saying that from the sandstone portion of this facies association, which we are trying to classify, 70% is hammocky, 30% is trough cross stratified. We would click on the save button, and all of a sudden the page on the right would again interactively update. So right now, our filter is showing us processes, and these processes entirely have to do with the physical structures that we put in. So all we said was we have a sand dominate interval. within a package which has a lot of hierarchy and a lot of cross-stratification in it. Again, from your knowledge of depositional models, very often if you see hierarchy cross-stratification, this indicates that there is storms in the system, so there must be a lot of waves in the background because we had a high percentage of hierarchy. Again, the decision system in the background is telling us that we must be in a wave-dominated scenario. Now, we have not told anything else, so all processes are possible, but the system has identified that we are in a wave-dominated scenario in terms of process. So notice that we have to do this for sandstone, heterolithic, and mudstone separately. Okay, all of those things again work together. So we would answer the questions, we would use these pop-up windows, and the final answer would represent kind of what the database is returning us based on our inputs. We can do the same thing with trace fossils. So if we expand the trace fossil button, we get to a menu which again deals with the same intervals, but now focuses on identifying basically the echology of the interval. It works in a very similar way. We have a button that tells us what, for the particular lithology, for example, a sandstone dominated interval, what is the overall bioturbation index? And then if you want to put in individual trace fossils, you would click on this Add Ichnogenera button. And it works in exactly the same way. You would go in, you would identify what trace fossils you observe. There is once again an integrated image atlas here that you can use. You would click Save. And then you would get the update based on what happened, what just came in from this filter that deals with trace fossils, in addition to the other filter which we never removed before. So at the moment we have two filters, as you can see. One is coming from physical structures, one is coming from ichnogenera. So in fact, if you scroll down, lower down in the page, you will actually get to see what the combined, based on our inputs about physical structures and echology that we just put in, what are the actual phases association element complex answers that apply based on what we just put in. Okay, so all of everything that we have seen so far has been a part of Sedbase, split up into separate modules that were never talking to each other very well. Right now, everything has been integrated into a single package. It makes actually kind of using these separate approaches of classifying intervals together very easy. And I think it's a much more kind of useful way of doing it once you get used to it, of course. Now, something else that we can use these modules is predicting architecture. Now, we did discuss making predictions about what happens in between wells in subsurfaces being a major challenge. Well, we can help a little bit at least with this. We have an integrated tool as part of these packages, which looks at parent-child relationships between local environments and regional scale environments, element complexes and element complex assemblages using wave terminology that we will be discussing a bit later on today. So we can use these relationships between parents and children to tell you about what other environments might be present in kind of adjacent to a well in the same interval, and what are the possible parent environments that might be present in an interval. So how do we do this? If we open, for example, the characterized environment, so we don't need to select any filters at all, or we could have selected filters. It works both ways. We would scroll down. We have gone to our grid view of where we are showing the individual phases associations. In this case, we can, for example, select one, FW mouth bar element complex. We make a selection. Now you will notice that as I do this, and I'm kind of going back and forth, all of these green dots appear. Now, every time you see a green dot in this dashboard, this would mean that this is a possible sibling architecture unit to what has already been identified. In this case, we're being told that if we have a WF mouth bar, it is possible that somewhere in the same system adjacent to us, we might have a mouth bar which is not wave influenced. Maybe we are in part of the coastline which is more protected by waves. We can have more wave-dominated mouth bars if we are in part of the coastline which is more exposed to waves. If we click on local and nearby, and we can take everything out which is not a sibling. So in this case, this was our input, and all of these element complexes are possible things that we might want to consider when we are building our conceptual model for what might be in the interval. It doesn't mean that they're there. So this is not giving you an answer. This is giving you a possible set of answers. Again, the main objective here is for us to think about, what are the possibilities in terms of deposition architecture we might want to think about. I mean, all this would very much kind of depend on the particular case study, how much data you have, etc., etc. This is a very useful thing to at least get you thinking about some of the things which you may not have considered. And so, for example, you have a wave influence mouth bar. In this case, you're being told, well, it is actually possible that you might have kind of wave-dominated portions of delta lobes, so somewhere close by to this interval. So it will be then your job to actually think about which of these scenarios make depositional sense. So this would be possible nearby, i.e. sibling environments. Another important question is, what are the possible parents? So what region of scale depositional environments can be a parent to what we just identified? To figure this out, you would click on the all possible button. So again, this is a type of prediction that we do. So if you click on it, you would actually see that you have two possible parent environment types. This is our ECA level, element complex assemblage. So in this case, you should think of this as part of a depositional system which is affected by the same process on a regional scale, right? So you're not thinking kind of locally what happens in a facies association and adjacent to it, but more what is the local what is the overall depositional environment which is housing all of these units. And in this case, you're being told that there is two possibilities based on what you just put in. Okay, so again, we had all these things before as standalone modules. Now everything works together. So the new characterized dashboard incorporates every single characterized environment, classify dashboard that we had before, in addition to all predict dashboards that we had. Okay, so this is kind of the main new addition that we'll be spending a fair bit of time on next webinar. In addition to that, we have all the stuff that we focused on last year for those of you that attended the webinars. The characterized environments update was kind of the second phase of this change of technology that we are doing in Sedbase. So let us now kind of go over the view analogs and dimensional data that we have seen before. Now to get there, you'll click on this view analog and dimensional data button, which will then open up kind of the main page, a very different looking dashboard, still following the same design. So we'll still have the same, basically, top menu. We still have filters on the left-hand side. On the right-hand side, now we'll have a lot of maps, and we also have charts as well. So how do you use this? In this case, for example, we are in the systems part, in the systems data set that is part of this dashboard. We have several data sets as we're going to discuss. These maps are interactive for the most part. So in this case, we have we can have a global map with a number of polygons shown. If you click on a polygon, a pop-up window would appear, which would show you the details of the actual system that has been mapped. This is an interactive map, so you can actually interact with this map itself. You can also get an expanded map view. This is the most useful to use typically. So if you're interested in an analog, you can very easily actually view it. Because this is an interactive map, you're actually allowed to tilt it, rotate it in any way you like. So a lot of time when we think about, what is the architectural variability of depositional environments, this type of data becomes very useful. So in terms of some of the stuff that is included in these maps, all of these maps have kind of a geomorphological mapping in the background. So we would have things such as crowbars, which would be shown in orange. In blue would be shown active and abandoned channels. In white would be shown beach ridges. And we would also have bathymetric contours. So the idea is that you can view an area and you can use this geomorphological information to make sense of the system in a much better way than just looking at the raw satellite data itself. Okay, so one of the things that you can do with this part of the dashboard is you can use filters. So these work in exactly the same way as the filters we were discussing on our characterized environments dashboard. So in this case, as a step one, you would use a filter. Based on the filter, you would get a set of results. And then you can actually view the results and kind of study the architectures of these. So you can select, let's say, a depositional process, and then you can view a number of systems that correspond to that depositional process. So for example, each analog in our database, we have 336 of them at the moment. Each one would have associated metadata with it. So for example, depositional process, tectonic setting, receiving water basin, drainage network, information about tides, bathymetry, gradient. So the idea is that you can try to answer as many of these questions as you can from the subsurface. You will then start looking at the right set of analogs for your particular area. And hopefully there is enough analogs in the database so that you can find kind of a suitable modern analog which teaches you what the architecture in the subsurface might look like. So the main objective of using these analogs is to use them as kind of as mental tools to think about, what types of architecture might be present, what is the natural variability of these systems. And again, we would have quite a few webinars that would exclusively focus on these topics. So we have filters that you can use, and then depending on filters, you can view maps, and you can also view interactive charts on any numerical filter that is included. We will see how that works a bit later. So in this case, let us illustrate what we just discussed. We once again have a filter. Notice this is exactly the same filter menu as we had, as the one that we used in our characterized environments dashboard. We are clicking the same button, so we would click WF. As we do this, the page on the right-hand side has updated. So if I go back and forth, you will see that all of the oranges and browns disappear. Only the yellows remain. Yellows in this case mean wave dominated. So we can actually zoom into an area. So in this case, we have the outlines of a number of systems which are classified as wave dominated on a regional scale. We have this very useful grid button, which is then going to show you all of these systems together in a single view. So the nice thing in this case is you can view many systems at the same time. You can decide which ones are appropriate, which ones are not appropriate. All of these are interactive windows again. So for example, what I always find very useful is to rotate the system so that they're all pointing in the same orientation. Sometimes, for example, in this case, I have rotated them and added a tilt to them so that we're sort of looking at them at a 45-degree angle. This makes it very easy to compare system. And again, what we're after in this case is understanding the typical architecture of a wave-dominated system, kind of getting a feeling for the natural architectural variability of these systems. So being able to compare them quite easily is very useful. You can actually select individual systems. You can filter them in different ways. You can select systems and only show the systems that you have selected. So there is a lot of stuff here. We will be discussing this in fair bit in kind of subsequent webinars that deal with depositional environments. Okay, so as part of the same dashboard, as part of the same view analogs and dimensional data dashboard, we also have an integrated channel belt database. So we actually have 4 separate databases that are part of the same package. To get there, we would close down the menu for systems, and we would activate the channel belt button. Now, notice everything has the same look and feel as the characterized environments dashboard. We are using on the back end kind of some of the same components which are building these things. So if you learn one, in a way, it helps you figure out the other. So in this case, what we have done is we have clicked on this channel belt dataset. The map has updated. So now we see a few areas with kind of red polygons and very different looking filters. Now, if we will zoom into an area, right now we have zoomed into an area. We have also added a feature which kind of gives us a 3D view of polygons. So right now we're looking at a system and we're looking at mapped channel belts which are included in the database. This is a number of channel belts that we have. So we have 2,000. So based on this filter, we have 2,486 channel belts. Okay, so for each channel belt, this is where numerical data becomes a lot more important, because very often in the subsurface, if you're doing, for example, object modeling of channels, typically it should be the channel belt that you need to worry about. This is the mappable unit in the subsurface for the most part, that the scales at least we are used to in the oil and gas industry. So in this case, we have filters. So you can very easily further kind of narrow down the selection of channel belts which are active. And each filter has an interactive button that shows you a chart. So what we will do in this case is if we click on this of this little icon, histogram icon that appears, a pop-up window would open up, and then you would get a live histogram, in this case of median width of channel belt. Okay, so keep in mind that you can do this for every single numerical filter in all of these dashboards. So if there is a numerical filter, you can always plot the data as a histogram, as a box plot, and as a cross plot. In terms of data, we say we have 2,682 channel belts which have been mapped from 32 systems. Describing the shapes of channel belts is not a straightforward thing. So one thing that was actually done is we came up with kind of an algorithm which helps us do that in a very consistent way. So a lot of our measurements are in fact quite accurate in terms of the stats which is available. How are the actual channel belts described? Well, we start off with our geomorphological maps, the same maps that we would be viewing if we are looking at the analog data set. So in this case, we have a system. We have mapped a number of active and abandoned channels and scroll bars using this system. We would focus on systems where this architecture is visible for data to be added to the channel belt database. We put an outline. So the channel belt itself, it would correspond to all kind of sediment accumulations that formed as the channel was migrating while being active. This is what a channel belt is. So in this case, we kind of have a shape that we can work with. We do this for the entire system. Okay, so we have systems with quite a few channel belts which are mapped as a part of them. Again, this is kind of a regional view of this. And then each channel belt, we will take it to that script that we were discussing. So the script would analyze the shape of the polygon. It would identify areas which have an anomalous shape. They are kind of highlighted in a different color. And they're ignored for example, putting in a center line through this body. So it turns out that if you don't ignore these bulbs that form, you get very strange center line shapes. So this is a very neat way to ignore kind of the unusual parts of the channel belt in terms of getting stats on its shape. So in this case, we can put in a center line. We can start looking at inflection points and again, kind of collect a lot of useful statistics which describe the shape of such a body. Okay, so channel belts you can directly quite easily use as kind of a source of data for object modeling. But another way these channel belt data sets are very useful is also from an analog standpoint. The idea here is that you can very easily kind of look at these fairly detailed maps and get a feeling for example, a system such as the op system would have large channel belts, small channel belts as a part of it. Many of these would be very, very difficult to map in the subsurface. So you can use these channel belt data sets also as kind of analogs for what type of channel architecture might you expect in a given area. So just as an example, this was kind of a conceptual model of a field that used the op data as kind of as an inspiration, but you can visually see that in this case we have large channel belts, but it appears that there is most likely more smaller scale channel belts which are not which should probably be included in the conceptual model. Again, this is how you can use all these data sets together and try to integrate it in a conceptual model so that we map the right things in our reservoir. So far we discussed when it comes to the modern analog and dimensional data dashboard, we discussed our systems data set, which contains, this is our main source of information for analogs. We discussed our channel belt data set, and now we would move on to our channel parameter database. So another data set which is part of the same integrated dashboard. So to access it, we would click on channels. So again, we would kind of activate this data set. The map is going to change again because we are accessing different sources of information for what is displayed on maps. So we have done that. We can see that we have quite a few areas with shown in red on the map. If we zoom into an area, especially some of these areas have a fair bit of data associated with them. So these are channels, points associated with channels from the Niger Delta that cover both fluvial and tidal channels. And in a little bit, we would see what those measurements actually represent. But the idea is that we actually have a global set. So if you're interested in shapes of actually active channels, so if you want to model mud plugs in the subsurface, or if you're curious whether, let's say, something that a seismic channel that you're seeing in the subsurface is an abandoned channel or a channel belt, this data becomes very useful to start answering some of these questions. The way this data set works is very similar. We have a number of filters on the left-hand side. So you can always narrow down your search based on these filters. In addition to that, we also have kind of the ability to show charts of anything that is numeric. So in this case, if you're interested in, let's say, clicking on this histogram icon and viewing what are the widths of the channels in our database versus the widths of channel belts compared to what we saw before, you can easily do that. So in this case, we kind of have a histogram which shows us a lot of data is kind of in a narrow range of sizes. Now, these charts are quite interactive. So one thing that we can put in a bin range, something else that we can put in is a bin number. So in this case, I have put in a bin number of 100. In this case, we just added 100 bins to our data set. And then we can use these scroll bars to narrow down the selection, that kind of the window that we are viewing. In this case, so if we are kind of interested in the distribution on the lower kind of scale of sizes in these data sets, which is where most data is, we can very easily do that. So again, at this stage, you can interactively change the bin number again. You can actually use a bin range. you get key summary of statistics on top. So you would always know what so for example, the median channel width in the entire database is 0.12 kilometers, so 120 meters. We can see what the 25th and the 75th percentile is, the minimum and the maximum, the standard deviation, etc. So every single numerical field in the database would have these charts available. So you can always study the data, you can always narrow down the data. So one thing that you can do is, for example, if you're only interested in channels which are less than 2 kilometers, you can very easily use a filter to actually narrow down this selection, and then the plot would only include these sizes of channels. So we have quite a few data here. This was a very big collection effort. So we have close to 90,000 points with data. And at each point, we have 4 different measurements. We have over 12,000 points with depth information. So in quite a few places, you can actually find how deep the channels are. We are mostly interested in the maximum depth in this case, because this best represents what will tend to be preserved in the subsurface in terms of channel belt width. So the point is that we have a lot of shape information, but we also have depth information. So just to give you a visual for how something like this works, and again, we will be going quite deeply into all of this content in the last webinar. But in this case, we have again used our geomorphological maps. We find a channel, we map inflection points. So all of the points in this entire data set are locations where the curvature of a channel changes. Let's say from going to the right to going to the left. At each location, we would measure the width of the channel. This was done by hand in Google Earth. We would measure the direct distance to the next inflection point. We call this LD. We would measure the along channel distance to the next inflection point. We call this LC. We would also measure the offset between the two, which we call amplitude. So for 90,000 points, these 4 measurements have been made. In addition to that, we have a lot of other data. So we have data on elevation, data on distance to channel mouth. So a fairly sizable data set that focuses on active channels. And again, it is very important for us to differentiate data related to channels versus data related to channel belts. The nice thing is that in this case, we have both, so you can very easily compare and contrast them. So how can data like this, how can it be used? Well, for example, one scenario is you can identify individual channels in a subsurface interval, kind of looking at the sizes of these finding upward trends. You can get a feeling for how big these basically channel belts are. Now, because we have depth information, you can start looking at, let's say, channel depths which are on a similar order of magnitude. So in this case, let's say that our average thickness was about 4 meters in this well. You can actually go in and you can see what do channels look like which are 4 meters deep. You can do this across systems. Again, for example, in this case, you can see that we have many channels which are kind of on this size, but this same system also has bigger channels which would be bigger. Again, all of this information can be very useful for us to kind of fine-tune the sort of visual conceptual models that we put together for a reservoir. Another direct application is
sorry, Brian, can I just ask a quick question?
Yeah, of course.
So do we have to be aware of anything when you're looking at depth of channels, risk compaction with what you're looking at on the log versus the modern analog? Is that going to make a difference?
I mean, so it will make a difference if you're looking at abandoned mud field, basically, a mud plug. For the most part, most of the channels that you tend to map in the subsurface would be sandy. So compaction would be, I mean, it would be a factor, but it would not be a big factor. But all of those things are things that you have to worry about. I mean, the unfortunate thing about using analogs is that they are always partial. So you should never just take data and use it. You should always think about what does it mean. I mean, this is why it's actually nice to be able to see where this data comes from, kind of visually assess. Is in this case I'm seeing a number of channels which are on this order of magnitude, but do I think that these channels actually fit my subsurface kind of the conceptual model that I have for the reservoir? I mean, should I add a new conceptual model or should I be looking at different data? So all of those things are things that we do unfortunately have to worry about it. So it is not easy to make predictions about architecture when you have little data. So channels are a very good example of that, because most channel belts are smaller than the spacing between wells. So very often we have to make a lot of educated guesses about how big those things are, what their shapes are, how they connect, etc. Okay, so for example, another way in which you can use this data set, imagine that you have some seismic channels that you can observe. Well, in these particular cases, for example, you can actually work out what the shape of a channel was. So this is the channel belt, entire body, but you can actually make a fairly educated guess what the shape of the final channel was. And at the moment you get a shape of a channel, you can then go to the database and start looking at similar modern channels. So for example, one thing that you can do is you can start kind of use this approach to make a guess about how wide the active channel is, how deep it might be, etc., etc. So again, information which can be used in many different ways, unfortunately, but it is useful that it's there. So depending on the particular question that you're trying to answer, there will be a lot of data in these databases to help you with these answers. So this is the sort of thing that you can do. You can actually almost map on seismic kind of shapes done in the same way as we collected the modern data, and then you can find modern analogs based on the same shape parameters. Okay, so we talked about systems, channel belts, channels. Another database that we have as part of the package is a mouthbar parameter database, again focusing on modern systems. You access it in exactly the same way as the others. So we would click on this mouthbar data set. The map is going to update. Now, because these mouthbars are hugging coastlines, very often when the map updates, you will not be able to find them very easily. So you actually have to zoom in a little bit to see where they are. So this is, for example, one coastline. This is the western coast of Colombia, which has quite a few mouthbars which were mapped. As with all of the other data sets, we have a number of filters of depositional strike extent, depositional dip extent, distance to adjacent mouthbar. All of these filters you can use to narrow down your search on the one hand, and then to get dimensional data based on these numeric values on the other hand. Now, it is important for us to understand how the mouthbar data was collected. Again, this was a fairly involved project where we went in, we looked into historical imagery in Google Earth in a system. So this is an example of one of these bodies that was mapped using this approach. So in this case, we start off from 87. What we're looking for are these wave breaker zones. Now, waves break when the water is very shallow. So very often in front of a channel mouth that we can see, we can actually know what at least the shallow portion of the mouth bar is. And the reason why these waves are breaking in such a strange way is because there is this shallow kind of sediment body in front of the channel mouth in this case. So what we do is we actually observe changes of where sedimentation occurs through time. So we are mapping the positions of these breaker zones in essence. So you can see in this case for over 30 years, there is a lot of switching around of depositional loci. Once we get to kind of to our analog webinars, we would be spending a fair bit of time with these data sets, kind of getting a feeling for how these types of mouth bars actually build and how they look like in 3 dimensions. But the main thing that we want to understand now is that they've been mapped in that way. So in a way, we've looked at where has sedimentation shifted in the shallowest possible water over a period of 30 years. So we map all of these ridges and then we kind of get a map like this, kind of a geomorphological map of former mouth bar positions. We will then take these maps, we'll put polygons around them, and this is what is going to build this mouth bar data set. So we can actually get dimensions of, what is their strike extent, what is their deep extent, what is the distance between these adjacent bodies. So we again collect a lot of stats. And then you can, for example, start comparing, what is the spacing between mouth bars in a tide-dominated versus a wave-dominated coastline? How are the shapes of these bodies changing as we change depositional process at the coastline? You can start kind of getting to a lot of neat answers by following this approach. Okay, so this is our modern data. We also have ancient data. This is something which has not been looked at for a very long time. This is part of our Wave Knowledge Base legacy product. Now, at the moment, you don't have access to it. You should have access to it by next week. So next week, when we run the webinar, you would actually be able to go to the former pages as well. They still work. It's just that I have to add a new domain and just do some technical things in the background so that we can view them. So one thing to note here is that we have ancient data. The key about the ancient data is that we take case studies, kind of well-known case studies, we reinterpreted them in our classification scheme. And what this then allows us is to actually compare and contrast a number of different case studies which have maps which are looking in exactly the same way, which are described in exactly the same way, so that once you get, let's say, shape dimensional data of units, we are sure that the dimensional data is not mixing together different unit types. Now we will talk about our architectural scheme in just a little bit, and we will illustrate why actually this is a fairly important step. This is the only part of the database which has not been updated yet. The plan is for basically next year, as we run these webinars, the plan is to have all of this ancient data and more ancient data added again as an integrated dashboard where all of these maps would be live, where again you will be able to interact with them in a very similar way to what we've done with the last 2 dashboards that were added. Okay, so this kind of takes us. Let me just one last thing I forgot that I've added. So on the documentation pages, the last page that we looked at was this shallow marine workflow. Well, immediately below it, you have a practical application section. So if you click on these practical application sections, you can actually view kind of my list of at least a selected list of practical applications of what you can do with Sedbase. This can be expanded, of course, but again, it's a start. So let us view some of the things that you can do. So you can interpret depositional environments in cored wells. We've already discussed that. You can predict depositional environments between wells. We discussed that. You can find depositional analogs. Again, we saw a few examples of how that works. We can create conceptual models. Now there is an integrated digital whiteboard that has been added to WebBase, which can help us do that. So you can actually pull in all information. You can select the number of analogs that you like, the classification kind of environments that were suggested. And you can directly even start drawing conceptual models of the reservoir, depending on kind of putting all of this information together. Again, the ultimate goal of this is develop more realistic static models. So we want to use all of these analogs, all of these sources of information to make better choice about ultimately what type of a model we build. You can obtain dimensional data for object modeling directly. something else which we have not talked, but potentially you can actually use mostly the modern maps for MPS training images. And you can interpret seismic horizon environments, which again, I saw an example of. So again, there is quite a few different things that you can do with Sedbase. It's because it's a package that is helping you with interpretation. It's a bit of an open book with how you can use it. So it is very important to know what is there, to know what data is there, what its limitations are, so that you can kind of pick and choose and pull the right types of information when you do this. Okay, so the very last thing that I want us to do in the lecture today is, let's say a few words about actually the language of the database. Now, this is a very kind of important core component that from the very beginning of the WAVE Consortium project was center stage. So what we actually did very early with the project, our objective was to build a database of shallow marine geobodies, and we very quickly realized that unless we come up with a very coherent set of terms so that we can refer to things in exactly the same way, we just end up lumping very different things together in the same categories, which just gives us almost unusable scatter of data. So what I'm about to present now is kind of the conceptual framework from which the entire kind of Sedbase project has grown based upon. So why do we worry about kind of, what do we mean by language? Well, by language, we mostly mean process and architecture. Especially in shallow marine systems, it turns out that the depositional process is a very big predictor of what architecture does in a given setting. To illustrate this, in this case, we have two large deltas. So we have the Irrawaddy Delta on the left, we have the Danube Delta on the right. Both of these are kind of continental scale big rivers. In both cases, we can see that we have kind of distributary channels which start avosing and switching positions. If you actually look at the architecture of the channels themselves, they're not the same, but they're not too dissimilar. And yet, if we get closer and closer to the shoreline, and if we get to the shoreline, we see very, very different architecture. And the reason why we see the different architecture is because the Irrawaddy is a tide-dominated system, so tides are present there, and they are a big factor in moving sedimentation around. Whereas the Danube, it unloads its sediment in the Black Sea, which hardly has any tides. So things here are kind of wave and fluvial dominated, depending on which part of the system you're in. So kind of a very important thing to realize every time you're working on a shallow marine system is that if you get the depositional process wrong, kind of early on, you're in big trouble in making predictions. Just to show you kind of another example, in this case, we have two wave-dominated coastlines. One of them is from Mexico, the other one is from the western coast of Colombia. In both cases, you can see that the shoreline is fairly smooth. So these are wave-dominated coastlines, but the bottom example also has tides in it, which are significant. And if you actually start kind of mapping these mouth bar bodies, which we were discussing, it turns out that they're a very big part of the architecture here. So tides are good at keeping channels open. They're good at kind of forming little tidal deltas in front of them. So it turns out that in the bottom case, even though this is very much a wave-dominated system, there is additional kind of architectural complexity, which we would probably want to worry about in a subsurface scenario. So just to kind of illustrate why all of this matters, this is the Danube Delta. This is probably my favorite kind of delta for illustrating purposes. The delta has both wave-dominated and fluvial-dominated portions in it. So in this case, imagine that we have a field which, let's say that we have a producing interval, a unit which was built that has the same architecture as the Danube Delta. This is the extent of our field. Well, it turns out that if we have a core here, we would see a fluvial-dominated interval. Right? And if we have a core here, we would see a wave-dominated interval. And the reason why this is important is because those things, first of all, can be fairly close together laterally. And very often, if we see let's say if we have a single core and if we see a wave dominated interval, very often we will be inclined that the entire package is wave dominated. So we would say, oh, this is a strand plane. The entire field just has a bucket of sand in it. But in this particular case, this would not be the case. So the reason why we want to worry about kind of all of these processes and architectural things is because in the real world, there is natural variability. So there is systems which would be entirely wave dominated, but there will be other systems which would have more than one thing in them. So just as a review, why are wave, tides, and fluvial processes important? Well, visually, this is probably the best way to think about them. So if we talk about these kind of n-member systems, which are affected by only a single process, n-member fluvial, n-member wave, and n-member tide, we can get scenarios like this, where we have a shape like this, kind of these digitate shapes for fluvial, very different shapes for tidal, very different shapes for wave. If we have two processes, things get even more complicated. So we can talk about two process systems, WF, for example. And we can also have three process systems. This is where things get most complicated. So if you're working in, for example, if you're working in the subsurface and in your core, you see evidence for waves, tides, and fluvial, you should be prepared that the architecture of this interval can be fairly complicated. So again, we will be spending a lot of time on understanding the differences between these processes. So this is just kind of a brief overview at the moment. So what are the process categories in Sedbase? So one thing that was done back in 2011 in an APG paper that kind of Bruce, myself, and Rachel Nansen put together, we actually came up with a schema where we said, let us actually give precise categories to processes. So we are using these codes. A one-letter code means one process. Two-letter code means two processes. A three-letter code means three processes. We look at the orders of these, and we know exactly what is a dominant process, what is a secondary process, what is a tertiary process, and we also know the number of processes. So we should be aware with these categories. They will be used almost everywhere in the wave knowledge base. And again, we will be discussing this next time in a fair bit of detail. Now, one thing that we should be very mindful of when we think about process is that very often we label a system of being of a given process, but we don't think about that processes can vary significantly within the same system. So there is actually an important architectural component here as well. Just to illustrate that, this is a system, the Frontera system on the southern part of the Gulf of, is it Mexico or America? Whatever the name of that Gulf is these days. So in this case, we have a very wave-dominated delta in the front part of the system. But you can see that there is actually a very sharp line. This is a former barrier that was there, a barrier island, and a very different process behind it. So this is the same system which has a switch from being very wave-dominated to most likely almost not wave-dominated at all. This is the same system. So we do have to be mindful that a system is not, if we call a system wave-dominated on a regional scale, there can be a lot of variability within it. Another example is, for example, very often we will talk about the fluvial dominated delta. So the Atchafalaya delta, which we will be seeing in later webinars a whole lot, and the Volga delta, which we will also be seeing a whole lot. Both of them are referred as fluvial dominated deltas. But the issue is that they're occurring on a very, very different scale. And in fact, if you look at the Volga delta in a way should be compared to the Mississippi delta in terms of scale, and the Atchafalaya delta should be compared to small parts within the Volga delta. So again, there is this natural hierarchy of architectural units, which unless we think about, can cause us to lump very different things together and come up with possibly incorrect conclusions about architecture. So notice that the Atchafalaya delta is on a very similar scale as small parts of the Volga delta, right? But very often we just use this term delta and we lump those things together. So it is very useful for us to, when we talk about processes, to also think about architectures. So it turns out that in shallow marine systems, there is almost kind of a natural breakdown of different scales of architecture units you can think of. And the moment you start thinking about these scales, these architectural levels, making predictions, communication becomes a lot easier. So something that was done in a 2013 subsequent paper is we put this scheme together where we introduced a nested hierarchy where we started a scale of sequence stratigraphy, basically. A TR sequence, these days we are calling those things RT sequence, so a regressive transgressive sequence. We lump all regressive parts and all transgressive parts in a single unit. We call this RICAS and TICAS. We then subdivide a RICAS into individual depositional systems. We call those things element complex assemblages. Again, do not worry about the names for now. We will keep seeing them throughout the webinar series. Within a depositional system, we can actually have individual delta lobes. We call those things element complex sets. Within a delta lobe, we can have individual complexes. So the deposition in front of the kind of the mouth bar area, the deposition adjacent to it. Within the mouth bar area itself, we can have mouth bar element sets and elements. So there is this whole hierarchy of units that we can use. And the key is that if we are using this notion of a hierarchy, first of all, we make communication very clear. So if I tell you that something is an element complex, this is the scale you're thinking of. Right? If I tell you this is a fluvial-dominated mouth bar element complex, I'm telling you precisely the scale you should be thinking of. You should not be thinking of anything regional. I'm just talking about a local scale. Whereas if you refer to something as a fluvial-dominated ECA unit, I know that you're talking about this kind of regional scale deposition. So in terms of common terms, this can be called an RT sequence. The RICAS, for example, is the regressive portion of a parasequence. ECA is very similar to a depositional system. ECS is very similar to a delta lobe. Element complex, we can think of it as a faces association. Elements, very often, for example, heterogeneities would kind of fall on this element scale. So the key is that we need to focus on the right scale so that we make the right predictions and we communicate more efficiently. So in terms of element complex assemblages, those are used in quite a few places in the database. We actually have little cartoons that are included. We already saw some of these during kind of the overview part of the lecture. Again, the nice thing about this is they visually represent the sort of scale you should be thinking of. So you're not thinking about deposition in front of a channel. You're thinking about a stretch of coastline that has a channel in it, but there is other stuff adjacent to it. So element complex assemblages, we can think of this as our regional scale depositional units. They are associated with a process. We can view them to make predictions about internal architecture, right? So we have a linear type and then we have a funnel type. Again, do not worry about the details at this stage. We would keep going back to those things over and over and over again, so they would make sense by the end of the webinar. So just to illustrate how something like this might work, the Danube Delta has progressed for the last 6,000 years from this location to the present-day shoreline. So this entire thing is a recast. There is actually a barrier island that was formed there during transgression. It is a very big process kind of boundary. So everything in front of it is influenced by waves. Everything behind it is not influenced by waves. We have this portion of the system, which is mostly wave-dominated fluvial influence. This would be formed WFECA. We have this part of the system, which is more fluvial-dominated wave influence. So this would be a FWECA. And then we have all of everything that is happening behind the barrier. Those things would most likely be entirely fluvial-dominated. And they're part of a kind of a funnel-shaped coastline. So we would call those things F-funnel ECA. Internal to at least one DCA, internal to it, we actually have delta lobes. So those will be called the element set unit. Element complex set units. Okay, so again, notice how there is a natural hierarchy thing here. We can focus on the whole. We can focus on an individual delta lobe. If you call something an ECS, I know exactly what you're talking about. There is no confusion there. Okay, and in this case, in the dynamic, we actually have three different types of ECAs present. So we have an ECA, an ECS, and a child of the ECS is this element complex unit. Now, the element complex unit is very important for us because this is the unit we want to use when we are describing core. So this is your local facies association in a way. So imagine that in this case, we might have a delta lobe with three different element complexes. If we have three different cores through them, the facies that we would observe would be different. So if we want to make predictions about architecture, this is the sort of scale we should be thinking of. Very often at the scale of our fields, the element complex would be most likely the key architecture unit that we would worry about if we are interested in kind of interwell architecture. Again, because those things are important, we have a number of cartoons, which we will be seeing in a number of places in the database. Again, those things are associated with process. So we can have a F mouth bar element complex. This is telling us that this is a part of a mouth bar dominated body of sediment only formed by the wave process. There is no waves or tides associated. So if we would use our dynamic map, we can actually define a number of element complexes. If we would focus on this area, for example, there would be an element complex associated with these mouth bar deposits, associated with the distributary channels, and then separate element complexes defined adjacent to that kind of, which are formed by sediment, which is moved from the mouth bar area by waves for the most part and shifts laterally. So notice that there is a hierarchy of units here. So if we focus on a single unit, we can talk about the entire package, a recast. This single unit is then going to be part of an ECA, which is going to be part of an ECS, which is going to be part of an element complex. So the nice thing about following this hierarchy approach is that we can always be at the scale which is most useful to us and kind of easiest to us for us to work with in terms of making predictions about architecture. So for example, in a cross-section view, let's say that there was a regional regressive package followed by a regional transgression. Well, if I tell you that something is a recast, and this is our regional most unit, I'm basically telling you, I'm talking about the entire system, in this case, the entire part of the system which prograded most likely over a significant period of time in seaward direction. Okay, so the entire regressive package. I'm not talking about facies associations. I'm not talking about delta lobes. There is just no confusion here. If I call something an ECS, we know that we're talking about delta lobes. So we know that we are on a smaller architectural unit. In this case, we will start thinking about, what are the boundaries between the individual delta lobes? Are there potential kind of heterogeneities associated with these intervals? Can they impact river flows? So notice that we are getting on a much smaller scale. In a mouth bar package, it turns out that what actually happens below the element complex, so in this case, this would be the element complex, this entire package, and in turn to it, we have these element set units, which are even smaller scale. In a fluvial dominated system, there will be a lot of kind of mud which is being deposited. It is very easy for it to drape sediment bodies. So very often there will be kind of important heterogeneities that can impact fluid flow in the surface that occur on this scale. So notice that by using hierarchy, you can very easily, in essence, switch between units, focus on the unit at the right scale. So if you're in a very wave-dominated package, and if you're fairly convinced that you're mostly looking at strand planes, much of the key architecture will be occurring at the recast level. For the most part, you would expect that there would not be much variability across, a few kilometers between wells. If you think that you have delta lobes in this system, even though parts of it might be wave dominated, things can get more complicated. So all of a sudden you have to worry about these ECS kind of complexities. If you're dealing with mouth bars, very often you have to worry about the smaller scale complexity. So all of that stuff can be there, and thinking in a hierarchical kind of framework is very useful for us to think about them in the right way. And again, we keep talking about conceptual models. this is a type of stuff that should go in your reservoir conceptual model. This is why you have to characterize the environment first. You have to think about all kind of possible solutions that you might want to consider. And then, which of these solutions require smaller scale architecture versus not requiring it at all. Of course, all of this will very much depend on the particular deposition environment, the type of fluids you're dealing with, etc., etc. Okay, so we can talk about this parasequence scale, delta lobe scale, mouth bar scale. Okay, so we finished this is the end of our lecture part of the webinar. Let us then do kind of a quick demo for the next 10-15 minutes or so. My main objective of today in terms of demos is, let me make sure that I pick the right browser. My main objective of today in terms of demos is not to go into any detail. For the most part, we are mostly after kind of getting a feeling for what is there. All of you have access to the website. You can access it on your own. You can play with it. There is fairly extensive documentation, as I mentioned. So, for example, if you go to, we refresh the page. Let's actually start from the very beginning. So go back to sedbase.com. So to access the Wave knowledge base, to access Sedbase, sorry, you go to our website, sedbase.com. That's the only thing that you have to remember. You would click on sign in. Now, because I've already signed in not too long ago, the system would remember me, so I would directly go in. But if you have not logged into the new platform yet, or you have not logged in, let's say, for a couple of weeks, there would be this login window that we mentioned. So as long as you have a work email and as long as you have signed up before, all you have to do is you put in your work email and your password that you had chosen when you initially registered, and you would go in. Again, if you have not signed up yet, once you click on this page, you would click on the little sign up button on the bottom, and then you will just follow the instructions. If there is any confusion, you would click on the documentation page. There is actually a sign up page that goes in a fair bit of detail about what exactly you have to do. You would get an email with an authorization code, which you will then put in a field that appears. You would click a button, which will then take you to the login page. And unfortunately, the way the system is set up, you have to log in again at this stage, but you only have to do that once, basically. And then you would be able to go to the knowledge base. Now, let me say a few words about the documentations themselves. This has been a fairly big effort. So the documentation pages have been greatly expanded compared to what we had before. So a lot of the stuff that I was discussing today is in fact here. So there is sections on depositional environment supported, sections on like what I was talking about, the limited data problem is discussed here. There is sections on depositional hierarchies, the various units that we are using. There is, if you're interested in, let's say, using the characterized environment dashboard, there is a section on that. So if you're interested in using these dashboards, you can just go in and kind of follow the instructions. Okay, so let us click on sign in. This takes us to the same characterized environments page. This is the default page, which opens in this case. As we mentioned before, there is filters on the left-hand side, which are interactive. So for example, if I decide that I want to tell the database what the depositional process are, like sometimes we would want to do that. We have looked at a core, we have decided that it's either WF or FW, and we want to tell the system that this is the types of units that we are dealing with. So notice that I click these buttons, everything in the display area got updated interactively. These things are buttons that I can click on if I want to. We scroll down. This is this new pie chart view that is available to us. Again, if you would prefer the view with the icons, it's very easily accessible. You just click on this on these grid buttons. There is menus on top which control what is shown. So for example, at the moment we're showing everything. So these are the units which have the designated categories that we just described. We have sibling units and we have all other units as well. Now, if you were only interested in showing local units and sibling units, you would click this local and nearby. If we're only interested in local, we will just click local. Okay. To predict architecture, we'll just click on this. We actually have two different ways of doing this. We will discuss that during the next webinar. But one thing that we can do is if I click on all possible, now it will run a query in the database and it will tell me what are all possible parents to everything which is included in this list. I do this, and in this case, we have two possible original scale categories. Okay, so we don't have tides in the system, so none of these would be tide. None of these would be tide influenced. Okay, so we can always refresh a filter by clicking on a refresh button. As I mentioned, if we're interested in using processes, we can do that. So I can, if we have looked at a core and we have measured that we have 70% fluvial dominated and 30% wave dominated, we can put in these numbers. The filter that is a bit more interesting to show is this one. Now, this is a version of something that we had in the previous version of Sedbase. Now, in this case, the way this works is quite simple. If you have this check mark, you have this X, and you have this question mark. Now, if we select a radio button on the level of the check mark, we are telling the database these are processes which are present in the system. So at the moment I said there is fluvial, there is wave, there is tide, and the system is actually, the answer that it's giving me is all categories which have all three processes together, right? So we have not specified whether something is wave or tide or fluvial dominated. So based on what we just put in, there is basically 6 different processes that are possible. Now, if I put in that waves dominate, I end up with 2 processes. Okay, now I can very easily, for example, deselect this and narrow down the search if I like. If we scroll down, we can again view all possible scenarios that are there. Okay, so let me deselect that. Now, something else which again should be probably shown is if we go to the next part of the page, classify by identifying physical structures. So in this case, we are working with an entire facies association in core, let's say a coarsening upward succession. There is a question about the grain size trend in the entire succession. We can answer it. And then individually, we will provide answers for each lithology within this interval. So if I click on sandstone, for example, we have a number of categories that we would be working with. Again, next webinar would be discussing this in way more detail. Now, what we can do with these categories is if we click on a box, it is almost like telling the database this little faces is present. And something else that we can do is we can actually put in percentages. So if I put in, let's say, 30% for trough cross stratification and 70% for Tamaki. And if I click save, now a query is going to run in the database, which has a very, very large table with several thousand relationships, which directly links the answer that I just put in to possible element complexes. So based on what I just put in, the database is telling us that these are the possible processes that occur in the interval, and these are the possible element complexes that are possible based on what we just put in. So notice we just gave an answer for a single lithology. We gave it very limited information, so there is quite a few possible answers there. But nonetheless, this is how this works. Now, if you are interested in editing back and kind of adding something to the data, all we have to do is we click on the same thing again. Everything is active again. And one thing that I should have also mentioned is that we do have these hand lens buttons. So if we click on one, there is actually an interactive image atlas that shows you examples of what these things look like. Okay, so we can keep this one open. If we then scroll down to the page, and if we go to the classify by identifying trace fossils, we can use another part of the module which works with trace fossils in a very similar way. Once again, we work with individual lithologies. In this case, all answers are tied to lithology, so we can give an answer for the rate of bioturbation. We can once again click on a button and then start selecting individual traces that are observed. If we click on save, this thing here gets updated. Now I didn't put in much information, so everything that I have put in is consistent with all of these answers, but the idea is that if you do a unit carefully, and if you kind of characterize all lithologies in terms of physical structures and trace fossils, very often you would find that the trace fossils are narrowing down the possible selections. I should mention that all of these relationships, for example, the trace fossil relationships were done by James McEachern, quite a renowned ichnologist. So he spent a lot of time on putting these relationships for us. So these are the main parts of the new module that I mentioned. Just as a visual, this is again the modern dashboard. We will be spending a lot of time using these dashboards in webinars, basically 3, 4, 5, and 6. So we will be spending a lot of time here. I don't want to spend too much time on it, but just for now, let us know that these are interactive maps. Let us know that we can once again actively select units here. So we have a number of filters that we can use. So we can add tidal range, tectonic setting, etc., etc. If we look at a polygon, we can click on it. These are live maps as I was showing. As you can see, it is super easy to interact with these maps. You can look at a system. We have a global geoformological map coverage, so you can actually zoom out, see what's happening adjacent to it. For the most part, these analog maps should be one of the most useful parts of the database, because you're given many examples of architectural variability for a given process setting. So for example, one thing that you can then do, we have already selected WF as a process. Now, if I click on this button, one thing that I can very easily do is I can find systems that I like. So all of these systems are classified as wave dominated. I can actually click on examples that I like. I can only show the selected. I can limit my query searches to these systems. I can even, for example, look for channel belts within these systems. Okay, so I think that this is all I want to do in terms of a demo at the moment. We will be spending a fair bit of time on all of these modules. And again, the very last thing that I should also mention is that there is a copy of the documentation here as well. So if I click on documentation, you get what appears to be the same pages that we saw on the public page, but there is a difference. There is actually a private component here. So in the future, a lot of webinars, kind of proprietary information, which we don't want to add to the public site, would be going here. But at the moment, for example, we have our facies models here. So all of the interactive facies models that you can get from directly in the modules, well, this is where they live. So there will be in the future sections on conceptual models. They can be shown live in 3D on the page. So there will be a lot of stuff. I have a lot of plans for the documentation pages in the future. The other thing is this XCaliDraw whiteboard. Now, this is just a service which is completely external to Sedbase, but nonetheless is very useful. Now, one thing that you can do is you can very easily, for example, do a screen grab from this page, add it here, add text to it, save your own copies so that you get a record of it. You can share it with colleagues, etc. The nice thing about this service is that it's completely open source. It doesn't communicate with any servers as long as you save local copies. So it's quite safe to use, and it's quite easy to use as well. And the nice thing is that you can actually draw your own maps directly here. So I'm personally using it a fair bit, and I find it very useful. So the idea is that you can use Sedbase, you can get information there, and then it can all kind of be put in the same place, in the same whiteboard, so that you gather all information and then you directly start sketching potential solutions and conceptual models, and etc. Okay, so I think that I would stop sharing right now. We don't have much time for questions, but there is a little bit of time in case there are some. Of course, you can always email me. I'm happy to have meetings with anybody who is interested in finding out more about these modules.